Howdy, Brian Vikings. We're here to talk about equilibrium. And here, right now, you're looking at an equilibrium. It's an equilibrium of water in the liquid phase and also in the gas phase. Now, what we're actually looking at is molecules that are actually vibrating enough and moving enough that they can actually separate and leave from the liquid phase and jump up to the gas phase, like these few molecules are just now doing. Now, some of them bounce up, but eventually some of them will make it back down into the liquid phase and they'll rejoin, okay? And so now we're all back to a liquid. And eventually some of them will bump back up to a gas and will just come back and forth. So the point is that we're going from a liquid to a gas in a forward and a backwards direction. And that is exactly what an equilibrium is a reaction occurring at equal rates. Take what you know about equilibrium now and ask this question. If both flasks were filled with 100 milliliters of water each, over time, what will happen? If you said that this one would evaporate and this one would not evaporate, then you are correct. What will happen is the water molecules will eventually come up and as a vapor and float around. I'm going to make my laser pointer as a water molecule. It'll bounce around, float up, and it will hit the top of the stopper and then come back and rejoin the liquid. But with this one, it will bounce around and come all the way out of the flask. And it will create an equilibrium with the room instead. And that's why it evaporates. Here, it would not evaporate. An equilibrium is officially defined as a dynamic condition in which two opposite physical or chemical changes occur at equal rates in a closed system. Just remember that intermolecular forces are attractive forces that keep molecules together, because we're going to come back to intermolecular forces. If you don't remember that, check out that previous video. Remember that the strongest intermolecular force is the hydrogen bond. The next one is dipole-dipole, and the last one is van der Waals or London dispersion force. I abbreviate this as LDF. Now, the stronger the intermolecular force, the harder it is to break the molecules apart. More energy must be added to overcome the intermolecular force so that the molecules can move past each other, which is melting, or separate, which is called vaporization or evaporation. So now let's talk about vapor pressure. The vapor pressure is the pressure exerted by the molecules of a vapor which are in equilibrium with its corresponding liquid. So let me make sure that you understand that it's the pressure exerted by the vapor, okay, which is in equilibrium. I think this picture really says it all because the liquid molecules are here and they say, hey, I'm so glad he's gone, he's evaporated, and then, oh no, we're back because they're they're back. And then these guys are going to get out of here too. That's the way equilibriums will work. So if we take our liquid molecules that are here, and I've put in a bunch of circles just to see the molecules closer together and in continuous motion, the vapor pressure is the pressure that's actually pushing those molecules down. It's the pressure exerted by these gases that are rejoining the liquid. Molecules with a strong intermolecular force will have a low vapor pressure. Molecules with a weak intermolecular force will have a high vapor pressure. That's because more energy is required to overcome the strong intermolecular force, so fewer molecules escape to the vapor phase. Fewer vapor molecules equals a lower pressure. So if I have fewer molecules up here, I have less collisions and less pressure on the liquid, and that's why the vapor pressure is lower. Let's talk about boiling. It's the conversion of a liquid to a vapor, and the boiling point is the temperature at which it converts to a liquid to a vapor. It's pretty simple, and y'all probably already knew that. Now, the compounds with a stronger intermolecular force will have a lower vapor pressure and in turn have higher boiling points. So the lower the vapor pressure, the higher the boiling point. Another term we need to know is the molar heat of vaporization, and it's the amount of heat required to vaporize 1 mole of a liquid at its boiling point, and it's measured in joules per mole or kilojoules per mole. Will have this symbol. It's a delta symbol with a capital H and an underscore VAP. That stands for the change in enthalpy of vaporization. We'll get into what those really are and what those really mean, but it is the heat of vaporization. So the higher heat of vaporization, the stronger the intermolecular force. So if we compare two different molecules, we have water and acetone. Water will have a low vapor pressure, acetone has a higher one. Water will have a higher boiling point than acetone, and it will have a higher molar heat of vaporization than acetone. That's because water has hydrogen bonding, and acetone only has the London dispersion force. So this one has a stronger intermolecular force. So just to recap, this is great to write in your notes, that the higher the intermolecular force, the lower the vapor pressure. The higher the intermolecular force, the higher the boiling point. And the higher the intermolecular force, the higher the molar heat of vaporization. Just a few more vocab terms to make sure we're aware of is that the normal freezing point of a substance is the temperature at which the liquid and the solid are in equilibrium at 1 atmosphere. The melting point is the temperature at which the transition from the solid phase to the liquid phase occurs. So the melting point and the freezing point are the same thing. Okay, it just depends on which way you're going. And then the molar heat of fusion is the heat required to the amount of heat required to melt 1 mole of a substance at its melting point. So we had molar heat of vaporization, and that was at the boiling point. Molar heat of fusion is at the melting point. Okay, and we'll get into this more in the next lesson.